Have you ever wondered like how LLM really works? Like how it can generate in a text or guess in the next word? So this is really a long history, and we're gonna check like how some of genius people came into the way, and from based on their theories that nowadays in the modern days that we have these LLMs. There was a time like long ago that a person named Andrey Markov, Russian, and he had a conflict with another person, or he was not like agreed with one other religious person at that time, and want to prove that everything is in a dependent system, right? So, and his concept is like the best idea how really we can predict the next word, right? So let's have a look, and let's take a very simple example. So I'm not going to take exactly his book because he worked in Russian book, and but we can still like deep down how this probability comes in play. Okay, so what he did, he read in a book, and from his book he took some sentences and trying to figure out how many vowels and consonants are there. So let's say we have a text, Berlin is the, right? And it's not exactly the same text he worked on, but we just want to check that his work, like what he was doing. He was like, okay, how many vowels are there? So when we write vowels, we know there is E, I, yeah, we have 2 times I and 2 times E, so 1 E and 1 I. And then consonant, we have B, we have R, we have L, and then we have N, then we have S, then we have T, and then we have H. Then he did his research, or when he was working on his book, he found out that there are 43% are vowels and 57 are consonants. So for example, in here, if we mark these, so we can say, okay, B is consonant, E is, let's mark it like this, R is consonant, E is consonant, and then E, N is consonant, I is vowel, S is consonant, T is consonant, H is consonant, and E is vowel, right? When it looked into this sentence, he, in his example, so he found that there can be a vowel next to vowel, there can be vowel next to consonant, a consonant can next to be a vowel, or there can be consonant next to consonant, right? What he found, so these dependency of letters, how letters are dependent on each other from the book which he read in that time, right? And from his example, he found that vowels to vowels are 6%, 0.06. So in those sentences, so first of thing, he removed the spaces. So let's imagine there is no spaces and they are written together. And now consent to consent was 19%, 0.19. And then vowel to consent or consent to vowel, these were 37.5%. Okay, so each of them 37.5. And he found out, so he did a manual work, that we have 43%, which is 0.43 vowels and 0.57 consonants, right, which is 57%. So he created a system to test like a vowel. What are the chances a vowel having another vowel? So taking a random, let's say, letter, so what is the chances that the next one is also vowel? So vowel having a vowel is equal to So we know that it's 0.06 divided by 0.43, the total one. And then he found that it's 0.13% chances. And similarly, so the probability of, so there's 100% chance that there is a next letter. We remove all the spaces already. Now, the chance that the next one is going to consonant would be then 1 from the 100% minus 0.13 is equal to 0.887%, right? 87%. And similarly, he said that consonant having consonant, so let's call it a C having C, is 0.33%, and C having V vowel is 0.67%. So he created probability of dependent event, a dependent system. So in the real world, it's also a dependent system. The weather tomorrow is dependent on weather today. The behavior of particles, how it's circling around, depends on the particle next to it, right? So at that time, maybe this was not so useful. So after that, when there was a nuclear weapons created, in that time, Ulam, the guy's name, Stanislaw Ulam, he wanted to simulate the chaotic dependent behavior of neutrons in nuclear chain reaction, right? Like how much the material uranium you need to create this chain reaction, right? So neutron, which is traveling and hitting the particle, there are chances that it just did not hit, so keep traveling, or it just leave or absorbed, right? This is like the possibility. Or it really did the fusion, so it really split into 3 particles, and they ran this into an electronic computer, the first computer on that time. They wanted to find out the probabilities of, like, what is the probability that we get the fission. So obviously it was depend on the temperature or the condition of neutron, how it is. For example, a fast moving neutron that could scatter is 0.30%, 0.50% that it being absorbed. We have now 20% that it's on its ongoing state, right? And this is 30%, and this is like 50%. But his idea was initially from Andrey Markov, right? The probability of finding the next event or dependent event. And then after some time, when we were in the era of internet, by the way, this their method, they named it Monte Carlo method. In the similar time, after when internet was there, so Yahoo was also working on their search engine, and they came up also with something called markup chain to rank the page, right? Like page a website, and if it's referring having dependency on, let's say it's A, on website B, it's 100% direct, and this is, let's say, 33 back to A and 33% to C, and okay, and this and goes to 33% here to the D, and this is 50% and this is also 50%, right? This goes here and this goes here, also 50%, right? So this looking current state to know what's gonna happen next, right? They had before a problem. They were doing words search, and people were like having literally some random words on their website, and they will just hide it, and they will appear on the page, and even it was not a relevant page. And they start like working on relevancy, like how relevant they are, and this was their markup chain model from that time. I don't know if they're still working on this one. So, and now we are after later on, let me make it open it again. In 1940s, there was a person called Claude, let me write the name, Claude, I don't know if the Cloud code name came from here. Shannon was his name, if you know about it, but I'm not sure. I haven't checked if the really Cloud name comes from here. So he was checking from Markov theory, this one, the dependent of letter to the next letter, right? And for example, if there's T and H, and there could be E or there could be B, right? I mean, for the sentence the, and the dependency was only to the previous one. He said, wait a minute, why don't we just take more than one letter and use more letter to know the probability of the next one? When he did it, then the result which came was like meaningless wording. For example, I don't know, we, fly, see, cat, on the earth, right? No meaning. But he found, but wait a minute, there are still some pieces which do have meaning. On the, we fly, right? And then what he thought, like, okay, what if instead of depending on letter, if we depend on words? And then what the result came, for example, the world of I don't know, animal to poet and house on sold. And more he experimented, and he found that more and more sentences start making sense, right? I mean, still the whole sentence does not make sense, but house on soul still do make the sense. And that's what you have seen probably when you're writing Gmail, etc., that sometimes the auto-completion was keep coming. And these were the basics, or the building blocks for LLM. Nowadays the formulas are way more complex. They are not like what I have shown you here. Because if you imagine, if you have this book and you feed all those words in a system, and you have way more complex and better formula, then you can really closely predict what the next sentence gonna be. Because nowadays we work with token, right? Working with numbers is way better than working with words. And nowadays you convert words into token, or letter, sentence, punctuation. They are converted into tokens, and from those tokens, then those formulas being applied, and then you can find out what the next word is. This thing, which is markup chain, this is also relevant in LLM. You would be wondering, okay, what play this role? This is nowadays, it's more like attention in LLM. So if someone I don't know, when we are typing, the cell is, now the cell can be like jail, that cell, or it can be a biological term. So if we have a context already before it, from the attention, LLM knows, I don't know, somewhere here, some blood mention maybe, right? And it knows that here, this refers to biological term and not the prison term. Now I will show you one more thing. Nowadays, LLMs are mostly built on transformer architecture, at least the GPTs, and it have multi-layer complex formulas to predict the next word. For example, if I type here, I am hungry and need some generate, right? It goes through all the vector, all the calculation, all the formulas, and brings a result more. And I have temperature 0.8. If I make it 0.2, food. The most likely word gonna be I'm hungry and need some food, not, I don't know, cat or sunset. Top K 5 means from these generations 1, 2, 3, 4, 5. I take only consider the 5 probabilities, and the higher one is what the result, right? And I could say take more, still food, because the temperature is also low. So temperature affect what is called logits, like score before probability, how randomness the result can be. 0.2 more strict, higher value more randomness, right? Then we have a top P, the probability, which mean that if we have more than one result, we should go till 50%. It can be 56 or that, but not going more than that, right? So here we are already 63, so we stop. These all are less than 50%, and we take the word here with 34%, right? If I have only one, like here 72, there's only one, it's already a match. If we have more variation of it, then we go 34, 14 plus 0.6. So we take from here the 55.31. This is the normalization. If I take it to 2, then we have a more numbers on the stack, and we go till, like I said, 50%, at least 50. So when you're summing up, if it sum up like 49, we still take the next one. So we fulfill at least 50%. And when there's only one match, and when we're gonna take it, and it's already going 50%, so we don't need to go to the next one and just take the first letter. And if I have more, like here, we take 41 and 15, so it's 0.56, so we don't need to consider other one. You see, they all are crossed over, so we don't need to consider them. That's how the top P, the probability of the next word, works. So that's how basically an LLM works. So right, like now you know how they came to an idea how you can predict the next word. If you have all the knowledge, all the data sets, for example, the person who read the book, he knows how many percent and what, and vowels and consonants are there, and then he know what could be the next word, and you apply now a bit more complex formula, but that's the base. Nowadays with this transformer architecture, converting into talking in a vector into number and doing all the calculation to figure out what could be the outcome. That's how basically LLMs work. Yeah, that's all, and we will catch up in the next video. Bye bye.